challenge in the additive is the size of the complexity of the part. So that's only challenge in the additive. So how to give the 100% coverage in NDT techniques. That's only challenge for NDT in the field of additive manufacturing. But I'll give an overview about it and I'll stress upon it, which you don't see in textbook. What typically on NDT. So let's begin the session. I restrict my work to aerospace materials and manufacturing. Look at any parts, even the automobile to aircraft to oil and gas industry. The part performance is decided by two factors, mainly the material behavior and properties. What is the material you use, which decides the performance of the parts. And coming to the material behavior is dictated by the properties of the material. So how a particular material property, take it aluminium, steel, or superalloy, or any kind of a composite, any kind of a material, whose property, which is the important element for deciding the part performance. How it is decided, if you see, typically three parameters will be looked into. One is the microstructure, which is the heart of the material, which will decide. Microstructure, which includes grain size, phases, second phases, and etc. etc. So everything as a whole I consider as a microstructure. This microstructure is the one which decides the mechanical behavior properties, physical properties of the materials. Second is surface pattern, or the surface features, or the morphology or the topology. This is also an important element when the part is exposed to the dynamic loading conditions or the contact loading conditions, or the conditions which are exposed to the corrosive or erosive area. Okay, so let's say I have a beautiful microstructure, I have a very polished surface. Can I ensure the performance? If you ask me, you cannot say, because the third element, which is very important, which is inherent inside of the material, which cannot be eradicated, which cannot be made it zero, which is defect. So there are various defects, starting with the nano scale or the atomic scale. If a particular atom misses from the lattice, you call it vacancy, or it displaces its position and going to some interstices. Okay, and group of vacancy removal or group of interstitial removal. So we call it as a different defects called the 0D defects, 0-dimensional defects. Then comes the row of atom missing, which is, you call it as a dislocations. It's a 1D defect. Then the grain boundary, which is a volumetric defect. Then comes to the crack. It's a 2-dimensional defect. That comes to porosities, 3-dimensional defects. So you have a variety of defects. So when you can have a zero defect in the material, when the entropy of the system close to zero, and when you cannot ensure the entropy is zero, you will inherently have the defect in the system, which affects the properties of the material. So you cannot have a zero defect material. So that is the first one.
Sorry to interrupt you, sir.
Yeah.
Sir, you are on first slide?
Yeah, I'm on first slide. So I speak a lot on the slides. I'll not just read the slides. So audience has to listen. No, there is no other way for them.
Sure, sir.
Yeah. So coming to I'm on the second point, third defects. Only I'm elaborating. I just want you to have an understanding about the defects. So defects cannot be made it as zero due to the very fundamental nature. So you will inherently have a defects which affects the properties of the parts. Some area defects are beneficial, especially in the plastic deformation regions. When you have dislocations, you can easily move the atoms, so you'll have a better deformation. So ideal lattice will not have a good deformation. So if you go to that, so the defects are also beneficial in some aspects, but it affects the property of the material. So you cannot eradicate, you can control, you can make it to the tolerable limit. So that is the only thing you can do. Okay. But how do I know a particular defects in the material tolerable or not? That's a very important elements to be answered. That is the reason NDT is invented, to detect the defects and understand whether the defects are in tolerable limit or not. I'll get back to you in your next slide on how to make a defect, how to understand a particular defect is tolerable or not. one important factor what you have to understand is, like as I said, like the microstructure is decided the properties. If it is a destructive properties like a tensile strength, fatigue strength, and creep strength, you use a conventional destructive testing. But the problem with the destructive, you destroy the sample. Whereas in NDT, you don't touch the parts or you don't damage the part surface or the internal features. Despite of that, you will understand and locate the defects and characterize the defect in the part. Okay. So different NDT techniques are available. We will see in the coming slides. I want you to note down the 4 fundamental NDT techniques which are widely used in the industry: liquid penetrant test, magnetic particle inspection (MPI), radiography testing, ultrasonic testing. Okay, you all as an academicians generally think that I have to look at the micro cracks, the things which are not perceptible to eyes or not distinguishable by eyes are the things you generally look at in your microstructure and discuss about it in a very lengthy way. But the industry never operates in that way. Anything which I could see in my naked eyes are only used as a criteria to fix that defect tolerable limit. Okay. So let's look at the resolution of the NDT techniques. Like if I use these 4 fundamental techniques, what is the minimum size which I can resolve comfortably by using these techniques? In liquid penetrant or magnetic particle inspection, 2 mm length crack I can see. That is the minimust defect I can see. And coming to the radiography, it depends on the section thickness. Typically 1 to 2% of the material thickness or 0.38 mm volumetric defects. Below that, defects are not distinguishable by eyes, so it is acceptable. Similarly, ultrasonic testing, the best and the most widely used is 0.8 mm FBH, flat bottom hole. Okay. Anything below that are acceptable, except in one part, that is a turbine applications where we go much stringent NDT requirements, that is 0.4 mm. Okay. So you look at these numbers. This is very important, which is grossly ignored by the academicians. You focus on some micro level cracks in the microstructure and explain the properties or property degradations, all those things. But industry works or the material specification or ASTM standard works on this. Okay. So this is kind of a Bible for you. Like when you manufacture any composites or materials, alloys, anything of the novel, as long as you have this level of defects, you should accept the material and go for the testing. That is what I try to emphasize. If you try to make the test process which is not achievable in industrial scale, there is no point in doing that research. Okay. So these defect limits, please keep in mind. Now, I said defects cannot be, I'm in second slide, defects cannot be ignorable. Defect cannot be prevented in any manufacturing process. There are defects, but my job of manufacturing process control is to bring the defect level to below tolerance level, acceptance level. Now the question comes, how to set the defect acceptance level? So you look at the aircraft designer or the automobile designers. How do they design the defects acceptance limits? First thing they will see the choice of the material what they make. Like let's say I choose a steel, typically used low carbon steel. Okay, what is its yield strength and what is its fatigue strength and fracture toughness? The strength will tell me or help me to fix the factor of safety. Fracture toughness will tell me, even though if I initiate the crack, what is the residual life I will be getting it, whether the material is tolerable to have a sufficient residual stress before failure or catastrophically fail. The second is stress analysis of the parts they do, because in your coupon level testing, whatever you do, you don't consider the geometry. Geometry like stress concentrations, sharp, edges. Other stress concentration like holes and other things you don't consider in the actual part in your material testing. Like when you do the tensile test or fatigue test, test you use the ASTM standards relevant like ASTM E8 or E21. Use it to derive the properties in a simple smooth geometry. You don't consider the stress concentration. That is the reason when I make the components, I'll do the stress analysis either by first initially using the simulation packages, and my part may undergo static load or dynamic load or cyclic load or thermal cyclic load, shock load, and whatever may be the case. So depending on the part's requirement, I do the stress analysis. Then I'll also locate in the parts what are the stress concentration regions, like notch regions or sharp corners, holes, or any welded regions, etc. Then the fourth important factor, what a typical designer look at it. Yes, I understand the geometry, stress concentration, material, basic material property. How about the service condition? Like, does it undergo the exposure of temperature or the corrosion or erosion kind of a things? If it is there, then the factor of safety will be added to that. Then I talked about in the earlier slide the minimum resolvable defects. Even in the minimum resolvable defects, what is the probability of detection? Okay, typically expected is 90 to 95%. So this NDT technique, resolution limit and the probability of detections, both are very important factors. Then let's say what kind of a design model I use it, whether the fail-safe design philosophy is fail-safe or safe life or infinite life or damage tolerant design. Let's say in the aircraft industry, typically they use safe life design. In Indian context, a very mature firm or the designers, they use a damage tolerant design. So when I use a fail safe or the safe life or the damage tolerant design, we use a different crack growth models, and we use the models to estimate the life and predict what is the critical defect size which leads to the failure very prematurely. So these are all the factors by using the FEM simulations that designer does. Then last factor is how often I do the inspection of the part. Let's say aircraft runs for 500 hours, it will come back and we do the overall. That is the inspection interval. So these are all the factors are considered to fix the acceptance limits. So if you look at it in the earlier slide, I am in first slide. Look at this radiography or the ultrasound. Though the minimum resolvable size is close to 0.4 mm or 0.38 mm, I never use this as my acceptance criteria. In fact, it is much higher than that. A typical critical component go for 1.2 mm size of defects in UT. And similarly, in the radiography, it will be about 0.5 or 0.6. Yeah, volumetric defects are acceptable. Okay. These numbers, I want, as academicians, I want all of you to note down, because when you do the research, you do the research to the industry, perspective, it will be meaningful. Despite you just start studying on the micro, crack level and discuss about the properties, which is of no use to the industry. This is the fact I just wanted to emphasize. Now I'll just hit to that my topic, non-destructive testing. So I'll just touch upon on the slides the important aspects. So as you know, in the NDT technique, irrespective of the material conductivity, material nature, you can apply NDT techniques to understand the defects present inside. Okay, the size of the defects you can characterize, and you can take a call whether it is acceptable or not acceptable based on the available ASTM standards or AMS standards typically used in the aerospace industry. People who are interested in NDT, okay, so you cannot be expert in NDT for additive or NDT for castings and forgings. NDT is applied to across all the discipline or across all the field of application field like aerospace, automobile, oil and gas industry, etc., etc. But the only difference comes what technique you got the certification, okay, and what acceptance standards you are following. They vary with the field to field. That's all. The all remains same. If you want to be a NDT expert or NDT specialist, you have to do ANST program or INST program, Indian based one or American based one NDT program, and you should get certified. There are 3 levels: level 1, level 2, level 3. As a student, you can do level 1. If you have a if you are working in the industry and 6 months exposure, you can do level 2. Then the level 3 is the expert level. After having 2 or 3 years experience in NDT field, you can appear for level 3. It is like a CA exam. Okay, so if you qualify that, you will be highly regarded as NDT specialist. So people like me or you who doesn't have certification are not allowed to do NDT test, not allowed to certify NDT test. And people who have a level 3 only are eligible to make the scheme for the NDT test. So this is something which you don't know, you don't find in textbook, which you should know. NDT has several benefits. Okay, one is to detect the defects or online inspection during the process, mainly used in the quality control. Of course, there is a cost efficiency here because you are able to detect the defects and discard the parts. You are not allowing the unfit part to go to the customer and fail in applications and create the problem for them. So that's why it's widely used in the safety assurance area. And you have a data, you can preserve it. In case you have any failure history, you can go back. Failure, you can go back and see the data and try to figure out anything else missed out. In aero industries, especially when we have a crash, aircraft crash or a helicopter crash, this entity plays a huge role that time. So some quick points on fifth slide, that is a superiority over the destructive testing like a tensile or fatigue or any kind of a common testing. Here I don't disturb the part, so there is no material loss. I can monitor on real time. Cost wise much cheaper. Most importantly, the entire part is completely inspected and there is no risk of doing NDT, and there is no hazardous environment while doing NDT, and quick results, immediately get the result, and it's more eco-friendly. These are the bookish information on the superiority over destructive testing. So today my focus on additive manufacturing, but I also want to give a flavor on polymer matrix composites, because if you look at the entire aircraft body, about 70% is 60 to 70% is carbon fiber reinforced plastic. 20 to 30% will be a metal. If you go to the engine, it is a reverse. About 95% is alloys, 5% is composites. So typically, a aircraft system or a space, even you go to the rocket, both these are ruled by alloys or composites. When I come to the alloy, additive is one process, but casting, forgings, other manufacturing traditional process also comes. So NDT is used for everything. It's not only for AM. So only challenge what I told you in the AM is the kind of a complexity of the part. In AM is very high. So how to ensure the complete coverage of the additive manufactured part is the key or challenge in the additive. Okay. But when you come to the polymer matrix composites, the complexity is similar to the additive manufacturing. Okay. But the kind of a defects you see, I have listed out the defects typically encountered. One is on geometry aspects, another one is on surface, another one is on material, fourth one is on the mechanical. Then whatever the manufacturing process you follow, it generates the defects. Similarly, on the polymer matrix, you have a fiber matrix. So what are the matrix related defects, fiber related defects? Then there is an interface between the matrix and the fiber. Then the process, especially in the resin, when you make the resins and when it cures, there are some voids formations. Then during the curing, there are some manufacturing related defects like contaminations, inclusions, and so on. And during the in service also, during the flight, there are some damages, like suppose a bird come and hits on the surface of the aircraft, leads to the impact damage. Then polymers are degrades with respect to time due to the moisture absorption, so environmental degradations. And similarly, metal corrodes over the period of time. So these are some issues which we call it as a defects can be found out by using the NDT techniques. But I want all of you to know, instead of focusing on the name of the defects, which you will, when you start practicing, you will understand. I want you to look at two aspects, like what is the geometry of the defects? It's a two-dimensional or a three-dimensional. Okay. Based on that, you can figure out which entity technique you can use it. Okay. When I go to the next slide, so you will be understanding that. Just to give a pictorial feel of what is the additive manufacturing defects. So if you have a regular, shape like a spherical pores and all, typically keyhole porosities. If it is irregular shape, it is due to the lack of fusions. Then at the interlayer, there are some cracks, delaminations, porosities. It's typically these are all you see in the additive manufacture. Okay. So because you use the heat to fuse the material, so you solidify the material. Whatever the defects you encounter in casting, solidification of the welding, you typically find in additive manufacturing. In addition, since it's a layer by layer process, at the interface between two layers, defects formations. Okay. And you use a gas, inert gas. If any failure in the inert gas leads to oxidations, contaminations, inclusions. So these problems you typically encounter in additive manufacturing. So just put up here. You classify the defects in two categories. One is the surface defects, another one is the internal defects in the part. Take any parts. Only these two are typically seen. On the surface, what are the defects? Again, in surface, you can classify into two categories. One is, which are open to the surface, which are hidden just below the surface, but it's not open to the surface. The one which are hidden in the surface is difficult to detect. Okay, there are some techniques I will tell you, which open to the surface is easy to detect. Okay, and defects comes through the process or the post process or your machining process, or even you use like a coating or finishing operation, that also leads to some process. And during any manufacturing process, any contamination comes, that also create the process. Okay, so different names are called, but out of these surface defects, typically we look at a crack, which is very dangerous. Any corrosion products is the second one. Then any oxide layer cracked regions, any decarbonized layers, any tool marks or heat treatment marks. These are the things that typically checked on the surface. Just to give a pictorial view, so how the different defects looks like in a transverse direction or longitudinal directions. But most of them are called cracks. Depending on its alignment, it is named in different way. That's all. So cracks are two-dimensional defects. Keep in mind, porosities are three-dimensional defects. To understand very easily, take a small stick, it's a crack. Take a ball, it's a sphere, which is three-dimensional defects. So you will be understanding those things. The second in the classification of defects is the internal defects, which are buried inside the parts, which is not known to us. You need to do entity to find out what kind of defects. Again, they are two-dimensional or three-dimensional. Three-dimensional typically are porosities, voids, shrinkage cavities, inclusions, either the non-metallic or the foreign material inclusions. So these are the defects which are called three-dimensional internal defects. And cracks of any form, hot cracks, solidification cracks, fatigue crack, liquidation crack, grain boundary cracks, okay, ductility tip cracks, punch cracks, incomplete fusion of the layer, interlayer, delamination. These all are two-dimensional defects. And structural anomalies are not detected through NDT, grain boundary defects or twin boundaries or columnar grain structure, because the size range is below the size range what I showed you. So we don't generally look at it. Yeah, segregations are looked at it mainly on the castings. And residual stresses are important now, stuck inside the defects. This UV light or a fluorescent light. That's all. So UV light is typically used for liquid light penetrant. Fluorescent light is typically used for fluorescent penetrant testing. So you see any kind of a surface defects which are open to the surface, like a crack or porosity, C-gaps. These are all the defects you can find. And there are different type of penetrants. Okay, if I use it fluorescent, it is a type 1. If I use it liquid penetrant, it's a type 2. If I want dual, it's a type 3. And different type of penetrants are used in the industry depending on sensitivity. One, after application of the penetrant, you have to wash it. Either if I use water to clean it or solvent to remove it or post emulsifiable. So if you want higher sensitivity, people go for solvent removal. And the developer also, there are different types. Either I can use a powder or some water washable developers or hydroscopic water washable developers. So when you get into the level 2, you will understand which penetrant or which developer to be used for which material and based on the sensitivity. So these are some images which will give you a feel about what is liquid penetrant or the dry penetrant. So the one important point which I re-emphasize is cracks or defects should be open to the surface. Whatever the defects, these are the important key points. Rest all are very simple. Apply the penetrant, clean it, apply the developer to take it out the penetrant which were stuck inside the defects. That's all. Through that you are viewing. Then second is magnetic particle inspection. So the one of the disadvantage in liquid penetrant is the crack should be open to the surface, which that requirement is not there in MBA. Crack can be just below the surface, not open to the surface also can be detected. But one limitation in this technique is, which is very important, is the material which we are inspecting should be ferromagnetic in nature. So put it simply for a non-metallurgist, iron-based alloys, cobalt-based alloy, nickel-based alloys you can check. Aluminium or titanium you cannot check because they are not magnetic. Okay. So here also I'll just take it very briefly. Let's say I have a defect. So as you can see the defects here. The fundamental idea is the defect should be oriented perpendicular to the direction of magnetic field of force. Okay. If it is oriented perpendicular, when it encounters any defects, that area there is a leakage of flux. When I put the powder into the surface, that all the powders will go and segregate in that area and give me the indication of the defect. Inclusion, anything can be checked. There are variety of methods. One is continuous methods, like you magnetize the component, you apply the ferromagnetic material on the surface. It's called continuous method. Or you magnetize and switch it off, then apply the powders, iron powders, that is a magnetic powders, to indicate the defects. That is called the residual method. Then, based on the powder application, ferromagnetic applications, you can classify. I can apply in the form of powders like a dry powder, or suspend it in some suspension, apply the liquid on the surface of the component, and I can also make these the suspended particles fluorescent by using the fluorescent agents inside. So it will be a fluorescent MPI or the visual. So likewise the different methods are there. So if you want to detect the very finest crack or the defects, go for residual method, wet suspension. Iron particles are suspended in the liquid or sprayed on the magnetized surface. So suppose I have a component like this kind of earlier component, the defect is oriented like this, and I detect by magnetizing in this direction. Suppose a crack is oriented parallel to the top surface, then I have to magnetize in this circular way. So any component, if I wanted to ensure the 100% coverage, I should longitudinally magnetize and circularly magnetize. So both the direction I should magnetize to ensure that my parts are completely checked. Otherwise, in one direction only you check. So to put it very simply, I have a cylindrical part. Let's say lengthwise I want to check. I have to magnetize diameter wise. Let's say I have defects aligned in the radial direction. I have to magnetize the longitudinal direction so that magnetic lines of force will be perpendicular to the radial direction. So both the directions you have to magnetize, inspect the parts. Once the magnetization is done and the inspection is done, demagnetization is very, very important. Otherwise, part when you supply acid is another danger. If magnetized part goes to the applications which involves any kind of electromagnetic, applications or the machining, there is a possibility for the accidents or the failure, because the magnetized surface will behave in a different way. So you have to demagnetize is another important thing which you have to understand. So cost wise, when you compare, MPA is relatively costlier, needs little more skill, but the advantage is even the closed defects which are in surface or subsurface can be detected. One rider is material should be ferromagnetic in nature. Okay. Now we'll go to the internal defects. So far we have seen surface defects. Now we'll go for the internal defects. That is radiography. Now in the internal defects, there are three-dimensional defects or two-dimensional defects. Three-dimensional means like voids, porosities, segregations, shrinkage, cavities are three-dimensional, because which will give you much higher energy. That's all. Okay. So the fundamental idea remains same. X-ray or the gamma radiography, fundamental idea remains same. So that is what I have put up here. Whatever the initial radiation, that is I0. When it passes through the material, it comes out. Okay. So depending on the material attenuation coefficient and the thickness it has passed through, the final radiation will be there. The regions which are not having the defects will have one intensity. The region which have defects have other intensity. So the intensity difference will give you the contrast difference. That will help you to detect the defects in two-dimensional. And there are variation in radiography. Presently, digital radiography is highly practiced because everything is digitalized, so you don't need the film. And higher level will be X-ray CT scan, computer tomography. The advantage with computer tomography, anyway, I'll be talking about it. The technique remains same. Some of the conscious facts about radiography is, as you know very well, radiation. So which is hazardous in nature. So you need to have a potential safety mechanism inbuilt in during doing this test. And test machines are very expensive. Skill is high level is required to do this X-ray radiography. Advantages, you get the permanent record, internal defects you can detect, any kind of a material depending on the density, you have to select the X-ray. Any complex geometry you can inspect by using the X-ray CT. So future X-ray computer tomography will be used because it can help you to get the complete view about component and its defects and its morphology and the locations and other factors about anything on the defects you can get very clearly in X-ray CT. So all the additive manufacturing companies employs additive X-ray CT for the internal defects detections. Okay, this is the only technique available to do the X-ray internal defects inspection. Coming to the ultrasound. So here I use the high frequency sound waves. I'll send inside the material. If I don't have defects, it will hit on the bottom of the surface and come back. Suppose if it encounters the defects, the distance it travels will be less. Okay, so depending on the distance where the defect is located, I'll be understanding the the presence of defect inside the material. Simple geometry like pipe, where I can access the internal regions, people use the through transmission technique. If I have a relatively complex shape, I'll go for the pulse echo. Advanced techniques are phased array UT or time of flight diffractions. These are the advanced techniques, especially phased array UT is used in the additive manufacturing industry. And time of flight diffraction is used to characterize the defect morphology, especially the crack morphology, mainly used in the welding. Immersion technique is used for certain material where when the sound wave travels from one medium to other medium, there is a thing called impedance. Okay, that when the difference in the impedance is very high, the problem of sound waves getting into the samples or the intensity of the sound waves which getting into the the material will be significantly reduced. Okay, so in order to reduce the difference of the impedance, people use the immersion testing like a water, because in air has a high impedance difference, it creates a impedance difference. So it means like a lot of scattering will be there in the ultrasounds. So when I use the water, the scattering can be minimized. So let's say I sent about 100% of ultrasounds, at least 90% intensity will get into the sample if I use the water. If I use only air, about 50 to 70 also it will get off. I mean, it will get scattered, only 30% of the energy will get into the system. Okay. So ultrasounds typically used to detect the internal defects or thickness of the material. These are the and any bonding issues in CFRP. Typically, UT is used. Okay. So any casting components you go for radiography, any forging components you go for ultrasounds. Similarly, composites also people go for ultrasounds. The reason is, in castings you get the porosities, voids, come the three-dimensional defects, whereas in ultrasounds you get the two-dimensional defects like cracks, delaminations, and so on. There are typically 3 scans are used in ultrasound: A scan, B scan, and C scan. So just imagine like this only. In the next slide I'm there. So you have a screen where amplitude is there and the distance from the surface or the time. Okay. So this is when it enters, there will be an intensity ultrasound or the amplitude of the ultrasound. As it progresses towards the material, it will hit on the back's end, then the reflected back and comes. There is a back wall echo. So if you look at it, the initial intensity is, let's say, 80% and the final is 40. What it's trying to tell you is this, 80 to 40, because when the material ultrasound travels inside the material, it encounters various phenomena. Scattering is the main thing which will create the loss of ultrasounds. Suppose I have a defect inside, the distance it travels will be much lesser, so the loss will be very less. So we'll have one more peak in between. Okay, so that will tell me, there is a defect at certain location from the surface. So I can find out the depth of the defect, and from the intensity comparisons, I can tell what is the size of the defects. That's all. You can do it in ultrasounds. So in the A scan it's like you have a cylindrical component kept diameter facing parallel to the surface, that is a horizontal directions. So any defects which are located at any depth can be checked in the A scan. Suppose if I want the cross-sectional view, I go for the B scan. If I want the top view, I go for the C scan. So if I employ A scan and the C scan, it is sufficient. I'll get the three-dimensional defects, a view of the defects. Okay, so both the metal industry and the composite industry, people use A scan and C scan to get the complete picture about defects. At what depth it is located, what is you can get it from A scan, and what is the planar area, you can get it from the C scan. So totally you combine these two information, you'll get the volume of the defects and the location of the defects. Okay. Distance amplitude correlation curve is important one. I will not go deeper into that. The idea is, industry, they will not go in point and check. They will establish this distance amplitude correlation curve. This is like a parabola. Okay. So let's say my designer says 2 mm defects and above is acceptable to me. Sorry, below acceptable to me. Will make the distance amplitude correlation curve for the 2 mm. So it will be like this. When I move the probe, where my intensity goes up, whether above the curve or below the curve, I'll see. If it is on the curve or below the curve, means defect level is less than 2. The moment my amplitude goes above the curve, means defect is more than 2. So that regions are marked and identified as the defect regions. Okay. So the advantage is with this technique mainly is any material, conductive, non-conductive, anything you can test. Okay. And no hazardous like X-ray diffractions, X-ray radiations, or gamma ray radiations. So safety wise, absolutely much better, much higher than the radiography. Any complex shape you can inspect, and cost wise cheaper than the X-ray radiography. But only it is sensitive to the two-dimensional defect like crack, delaminations. Pores kind of a volumetric defects, it will not be. It cannot detect because When the ultrasound reaches the three-dimensional defects, it will go to the pores, get it diffracted inside or the scattered inside. The energy which has to come out and reach the probe will be much minimal, which cannot be detected by the transducers. That is the only thing. Okay. So, and this surface preparation of the sample is very important. Okay. You need to have a very polished surface. Then only this technique will be much more effective. And the skill requirement for this is much higher than the X-ray radiography. Just to give a feel how the standards on the ultrasound. So I told you, right, defect level. So this 1.2 to 3.2 are the mm. Okay. So these are the class. So what designer says, I want AA class or A1 class or A class or B class. So my any single discontinuity or defects I find should be lesser than 1.2 for AA, and any multiple discontinuities. Like how do you classify single and multiple? If the distance between two defects are greater than 2 times of the 1.2 mm, that is 2.4 mm. The distance between two defects should be greater than 2.4 mm. Then these two defects are considered as a single discontinuity. If they are placed within that distance, then they are called multiple discontinuities. And this, when I encounter two defects very close to each other, each defect's size will be measured, and which should be less than 0.4. Then only it is acceptable. So this is a very important criteria. They use it in UT to certify the material or by the NDT experts. And FBH means flat bottom hole. So this is a calibration block. There are calibration block to establish these flat bottom holes. So I'll not go deeper into that. The standard name is AMS, Aerospace Material Specification 2630B. So when you come to the industry, you'll be able to understand what is it. And what are, for the academicians or the researchers, what are the advanced NDT? There are variety. I'll just quickly touch upon the important facts on the ultrasounds of future NDT techniques, which are not employed currently in any aerospace industry or any industries in India, automobile industry. These are there as a technique developed in TRL level 1 or 2 is there, still not employed extensively. So laser ultrasonics will be future mainly for the complex shape parts. So you can say for additive, it will be a future to detect the defects inside the parts, any complex shapes. Because it's a non-contact method, you don't need to keep the probe. You send the laser, and that laser create the laser pulse will be fired on the surface. This will create the ultrasounds inside the component. And usual UT, whatever I told you previous, will be used when the ultrasound is generated inside, and whatever comes out will be again captured through another laser, and it is analyzed in your CRT screen to find out the characterize the defects. The only advantage is any kind of a shapes, complex shapes I have, I can apply this LUT because I don't need to keep the probe on the surface of the parts. So any intricate internal channels can be easily inspected, irrespective of the material, whether it's a composites or metals. You can use a laser ultrasonics, but these are all in conceptual level. I have not seen any machine in any industry so far. So some quick advantages, if I have to tell you, no contacts, no coupling agents are used like oil or water, high resolution compared to the traditional AUT, versatility, high speed inspection. Limitations still in TR level 2, cost is very high. Still there are no standards or the expertise available in the industry in this area. Then process compensated resonance test. So here the idea is I exit the part mechanically by tapping or through vibration or impulse. That, let's say I have a component which is in the acceptable level of defects, that act as my standard block. Okay, the resonance spectrum will be my standard block. Now let's say I have fabricated the new part. I don't know whether defect is there inside or not. Now I excite that part with a tap or impulse or the vibrations. And based on its natural frequency, I generate the resonance spectrum, and I'll compare this resonance spectrum with the standard resonance spectrum to identify is there any issue. Okay, with respect to the defects or the geometry issues also can be understood, or internal, microstructure issues are there or not. Okay. So it's more of the comparison method. That's why it's called process compensated resonance. Resonance means, you resonate the component based on its natural frequency. So that's all. This is in the conceptual stage. Here, it is again a ND non-restrictive, because I just excite. I use a sensor to capture the resonance. So advantage is it's very fast and fully you can automate it. Just keep the sensor and excite, and just everything will be done through the computers. People claim that it can be used for the turbine blades kind of complex shapes, or the engine components and powder metallurgy components, and so on. Phased array UT is an extension of the conventional UT. So instead of having in the transducer one single element of piezoelectric material, I have multiple crystals inside. So I generate the ultrasounds, like many rays of ultrasounds, which can be automated or optimized based on its phase and time and amplitude. So I'll get the rays of a different range, which can be swept across a sample and get this information of the defects or thickness quickly in one shot. So that's why it's called phased array. I mean, array of crystals are kept in the transducer. So as you can see, dozen of piezoelectric materials are kept. Each emits ultrasounds in a different phase and amplitude, and I can also play with the time delay. So I can steer the beam across the sample and get the information about internal structure of the material in one go. So that is why it's very popular in the weld inspection, corrosion inspection, aerospace industry, nuclear industries. So the advantage is I get the detailed high resolution image. I can use the angular probe for the angular inspection. I get the real-time data storage and retrieve whenever I wanted. Relatively higher sensitivity. Even I can go up to 0.2 mm, I was told. And most importantly, it reduces the false positives. I mean, this is very important for the NVT point of view. Positives should be properly detected. Good things should not be categorized as the negative and rejected. So that occurrence is very, very less in pulsed array UT. But of course, any new techniques are high costlier, and skill levels and the surface preparation in the UT are very high. So these are the general limitations. Thermography or infrared thermography, just to put it simply, only surface defects you can detect in thermography. The idea here is you send the IR radiation on the surface of the sample, so it creates the thermal spectrum, because any hotter body emits the IR radiation defect on the surface. The heat transfer in the material will get affected. That defect either trap the heat and cool the regions, or emit the heat and make the region more hotter. So either it will be a colder region or the hotter regions. So when I have a standardized thermogram and your new part thermogram, you just map it, you will understand. Wherever I get this disturbance of the temperature regions, which will help me to the temperature difference regions, which will help me to identify the defect regions, like whether it's a crack or voids or any corrosions, you can understand. So advantages like other advanced techniques, real-time data, full area I can cover, no contacts like fluorescent penetrant or magnetic particle inspection. Okay, and flexibility. Most importantly, portable. I can take it to the on-site and inspect my pipes also. Limitations or surface condition sensitivities. Rough surfaces you will have a problem, and environmental factors, and you need to have a sophisticated heat sources to create the make the either passive thermography or active thermography machines. Yeah, X-ray CT is the one I was telling you, but it is nothing but the extension of the existing UT. Sorry, extension of existing X-ray diffraction, so X-ray radiography. So same X-ray source will be there, pot will be there, screen will be there. Only thing is, everything is automated and computer algorithm will be there. So you will take the 2D scan, and all the scans will be sent to this algorithm, which will stitch into the 3D scan, 3D image of the part. So here you see, suppose a traditional radiography, I will get the 2D regions. Suppose this hole will be seen as a rectangle, but this hole can be seen as a hole in X-ray CT because I will take the multiple shots and stitch all the images. That's all. The advantage is high resolution. So there are claims that up to 40 micron meter level I can detect the defects. And 3D visualization of the image, defects, where it is located, even the surface roughness you can measure, and density of the material you can measure through the X-ray CT. But importantly, very few machines are available in the country, no standards, high cost, radiation safety is one issue in the radiography, and size limitations. What I understand is about half meter by half meter by half meter level, machines are currently available. Acoustic emission test, it's like extension of another UT. What you do here, you keep the sensor on the part, okay, and subject them part to the some kind of a deformation, which is allowable deformation, the stress. What will happen is, if any existing defect is there inside, okay, which will open up, propagate, or any existing problem like a corrosions, this existing problem will respond to this acoustic emission and may make us to detect through our sensors. That's all it's happening. So it is not the passive entity technique. It's more of the active, where you send some external stimuli to that defects will respond to that stimuli. That stimuli will be captured by the sensors. Okay, and it needs sophisticated computer algorithms to get these signals and convert the signals to the electrical signals and interpretable. So it's mainly used in the heat exchanger or the nuclear industries, where I need the online inspection. And corrosion is a thing which can be easily detected through acoustic emission. Time of flight diffraction is again an extension of UT. So here you use the angular probe, send the UT signal. If any crack is there, it diffracts the ultrasound get diffraction. This diffractor razor will be captured on another side, a transducer, and analyzed to get the crack geometry, or you try to characterize the crack, where it is located, what is the shape of it, by using the the inputs of diffracted data. That's all it's happening. It's used in the industry in a very currently in a very minimal way. Assuming there is a crack inside, which is we are known, we wanted to characterize the crack, then we use this technique. Time of flight diffractions. So that's the way it's there. Like you have a transmitter, you have a receiver, you have a crack. So at different angle, ultrasound will go and hit and diffracted. Based on that time I take to reach the receiver, the information, based on that information, the crack will be characterized. So it's a high sensitivity is one of the biggest advantage. So micro cracks can be easily detected, but I have not seen anyone using in the industry. It reduces the false positive, because any advanced technology is the aim is to reduce the positive false positives. You can accurately characterize the size of the defects, high resolutions, and everything is automated. So there's a good amount of data acquisition and image formation using the sophisticated softwares. Surface preparation is important because you keep the transducer on the surface. It's a contact method, and only limited access and complex shapes, it is difficult to characterize the defects. Laser shearography, it's again it's based on the laser. The idea here is I send the laser signals onto the surface, okay, which will deform that surface regions. Mainly it is employed for the composite kind of heterogeneous materials, where I have two different material and I want to inspect the interface or the bonded regions. I use this laser shearography. It's mainly meant for the surface and subsurface effects. Okay. So you have to just illuminate the surface with a laser beam and create the electronic speckle pattern, which are created and which you record through your camera. Again, you subject them into the controlled stress, and you have a standard image of the speckle pattern, and the speckle pattern what you sample with the stress, and just compare it, and this interferometer or interferograph will reveal the regions of stress concentrations. Okay, differences that will help you to identify the difference. Again, I'm not saying anything usage of this in any industry. These are all the bookish information or the research information. So what I understand is TRL level is not enough to get into the industry. Eddy current test, yes, it's employed in the industry, but in the aero industry, its usage is very minimal, because only the conductive material can be tested. But since I have a better technique like fluorescent or MPI, people prefer less eddy current test. The idea here is like you try to develop the eddy current on the surface of the sample. So how to develop? You have a transducer, you send the electric current, it creates its own magnetic field. When the one conductive material is brought close to the another conductive material, it creates the eddy current, and that eddy current also creates its secondary magnetic field. This primary magnetic field and secondary magnetic field, if I don't have a defects, so it will be in certain way. When I have a defects, this secondary magnetic field will get affected, which will affect my primary magnetic field inductance impedance. So from the impedance, the defects are characterized. And again, there are variety of eddy current test. Conventional pulsed current, if I supplied its pulsed eddy current, if I keep more number of coils, like array of coils, then array eddy current. These are also called remote field testing, because it's a portable testing machine, so I can carry to the for the pipe inspections. And if I wanted to check the internal region, so I can use a rotating probe technique. So there are many are available. Mainly you see in the oil and gas industry, its usages. In additive field or the aerospace, not come across eddy current technique usages. But this technique is well established. Certifications are available for that, and other industries, they exploit this technique for inspection of that part, mainly for the surface defects. Even conductivity of the material you can measure through that, thickness of the material you can measure through eddy current testings. Okay. And coating industry also, it has a very good set. When I have a non-conductive coating on the conductive material, if you wanted to inspect the non-conductive regions defects, this is widely employed. The reason why people don't choose in aero is the skill of operator skill requirement is very high, and cost also relatively higher than the other indicators. And it's only limited for electrically conductive materials. Another novel technique which is recently popping up in the NDT area is terahertz imaging. Like the EM, electromagnetic waves frequency should be much higher than the ultrasound range. So in the terahertz range, non-ionizing waves are used to inspect the part. It's a rapidly emerging technology, especially in the composite industries. Currently used in the medical field and pharmaceutical and semiconductor area. The idea here is this terahertz rays are passed like an ultrasound inside. There are two modes you can use it. One is in the transmission mode or the reflection mode, like ultrasound, pulse echo or the through transmission. If I have a sample thickness is very small, then I go for the transmission. If I have a thicker part, I go for the reflection mode. Okay, so here you can detect the internal defects, mainly the voids, cracks, delaminations, inclusions, including the coating defects. Okay, the sensitivity of the technique is much better than the ultrasound, because I use a very high frequency. That's all. What is the difference between this technique and the UT technique? Since it's very high frequency, it's non-ionizing, so it's safe to use. Currently is used in the non-conductive material, because when you have a high frequency, the energy level is very low. Okay, when I use it in the metal, the scattering is very high, and the resolution is very good. And most importantly, it's very sensitive to the moisture and density. So that's the reason in the polymer area, that's the polymer matrix composite area, it's extensively researched. Okay. Because of the high frequency, the penetration is very less in the metal. expensive, non-standardized yet, no standards are available, slower than any techniques. It isn't tier level 1 or 2, so the limited maturity so far. So these are I have for you to give a comprehensive view. I think I spent about an hour, started at 9:10, closing 9:10. Thank you for the opportunity. So any questions, I'll be happy to answer. My special thanks to Dr. Yashwant and Dr. other organizers of this event. Any questions, I'll be happy to answer.
Very much, sir. We have one offline participant who is asking one query from you.
Yeah, please.
First of all, good morning, sir, and very thankful for your insightful presentation. Sir, I have a small query that out of these all entity technique, what technique that we can use to measure the residual stresses that we generally, and how to mitigate them during the IT manufacturing?
See, residual stress is nothing but the stress induced by the process whose value is lesser than yield strength. Then only it's called residual stress. Okay. So people use X-ray diffraction typically as a non-destructive tool to examine the X-ray, characterize the residual stress. You can go for a hole drilling method by using the strain gauges methods, but these methods are destructive methods, so people don't use it. Either you fix the interferometer or the strain gauge, you can you can measure the residual stress, but it is not advisable because it's a destructive. So only technique available for temperature thermal gradient. That's one way to do that. Or I preheat the powder and spread it on the powder bed. That is the second way I can do it. Third way is I do the scan, I finish it on the top layer where the residual stress will be there, because all this residual stress surface is nature. I'll rescan it with the lower